Mm, Let E be a countable set. Then E is a level set with mu of E is equal to 0. In this proposition, you see two properties of mu. Let mu be a measure on an algebra F, okay? And A, B, A1 to A car are the members of F, be the members of F. Then we have this property and this property. You must memorize the properties of measure, okay? In previous session, we had some properties of a measure. Here, you see two properties of measure, okay? The first property is monotonicity. Monotonicity. What is this property? If A is a subset of B, A and B are the members of F with this condition. A is a subset of B, then mu of A is less than or equal to mu of B. Okay, this property is called monotonicity. I want to prove this property for you. See the next slide. By assumption A is a subset of B. Let A be this circle, this small circle, and B is bigger and containing of A. Okay, this section is B minus A. By this shape, it is clear that B is bigger circle is equal to A small circle union B minus A. Okay, B difference A. Okay, and it is clear that by this shape A and B minus A are disjoint sets. Okay, so by finite additivity property, I told this property in previous session. Finite additivity property mu of B is equal to mu of this set. It is equal to mu of A plus mu of B minus A. Okay? Why? Because A and B minus A are disjoint. Okay? And by this property, we have this equality. It is clear that this sum is greater than or equal to mu of A. Why? Because the mu is positive. This is positive. So the sum of these two terms is equal to of mu of A. Okay? So we obtain mu of B is greater than or equal to mu of A. Please see the part B. Previous slide. Finite subadditivity, not additivity, subadditivity. Finite subadditivity is mu of A1 union to A car, A1 union to A car is less than or equal to mu A1 plus mu A car to mu A car. Okay, this is an inequality, not an equality, because A1, A2 to A car are not disjoint necessarily. Okay, if A1 to A car be disjoint set, then we have equality here. Okay, and then this property is called finite additivity. But we have an inequality. See its proof. First, for section B, we want to prove for two sets, A and B. For arbitrary set A and B, we have this shape, not this shape. For arbitrary A and B, please notice, okay? By this shape, it is clear that A union B, it is equal to A, okay? Union B minus A. and it is clear that A, B minus A are disjoint. Okay, by this shape it is clear. So we again use this property, finite additivity, and write mu of A union B is equal to mu of this, and it is equal to mu of A plus mu of B minus A. Okay, here I add this term minus this term. Okay, these two terms, mu of B minus A. See here, B minus A is this section, A intersection B is here, A intersection B is here, B minus A is here. And we see that this set and this set are disjoint. Okay? And the union of this set and this set is equal to B. Okay? So, mu of B is equal to mu of B minus A plus mu of A intersection B by finite additivity. Okay, so this two term is equal to mu of B. I write mu of A instead of these two term. I write mu of B minus mu of A intersection B. It is positive. This term is positive, so this side is less than or equal to these two terms. Okay, so for two set A and B, arbitrary A and B, we obtain that mu of A union B is less than or equal to mu of A plus mu of B. Okay, for two sets. Now, if we have three sets, A1, A2, and A3, then by this discussion, we have mu of this union is less than mu of A1 union A2 plus mu of A3 by this discussion. Okay, and it is less than or equal to mu of A1 plus mu of A2 and mu of A3. And we see that the section B holds for three subset of omega. Okay, three sets. Okay, assertion for coset is generally obtained by induction, and it is easy. Please see this proposition. This proposition is a proposition that I told you in previous session. Here you see two another properties of measure: finite additivity and monotone continuity from below. What is finite additivity? For two sets A1 and A2 with this condition, in fact A1 and A2 are disjoint, we have mu of A1 union A2 is equal to mu of A1 plus mu of A2. It is clear that by this property we can this relation for three set, for four set, and in general for n sets. Okay, you can see this property for n sets instead of just two sets. Okay, what is this property? This proposition is taught in previous session. I repeat this proposition here. Okay, monotone continuity from below. In this property, please notice, in this property, we have a chain, increasing chain, A1, A2, A3, and so on, with this condition is called increasing chain. Okay, A1 is a subset of A2, A2 is a subset of A3, A3 is a subset of A4, and so on. Okay, for an with this property and with this condition, if f here f is an algebra, if f is a sigma algebra, you can remove this condition. Okay, F is a sigma algebra, then you can remove this condition. Okay, so for an with this property, we have mu of union of an is equal to limit of mu of an. This property is called monotone continuity from below. You must memorize these properties. Okay, after this proposition, we have this proposition. You see two another properties of measure. Monotone continuity from above. See here, from below, from above. Okay, in this property we have an with this condition. Please compare this condition and this condition. These two conditions are conversed together. Okay, it is here an. It is a decreasing, non-increasing, decreasing chain. Okay, for example, A2 is a subset of A1, A3 is a subset of A2, and so on. This is decreasing chain, and we have mu of A. A is equal to intersection of an. Here we have union of an. Here mu of intersection of an is equal to limit of mu of an. And here we have another condition, an extra condition. Okay, what is this condition? Mu of a and z is less than infinity for some NCF. Okay, so in this property, monotone continuity from above, we have a decreasing chain with this property. Then we must have this relation. What is the countable subadditivity? In the previous slide, we had finite subadditivity. This property is countable subadditivity. An is a sequence of sets in F, not necessary disjoint. Okay, not necessary disjoint. With this property, if F is sigma algebra, you can remove this property. Then we have this inequality. The mu of union of An must less than or equal to the summation of mu of An. Please see this exercise. It is easy and it is very, very important. Let omega be a non-empty set and, excuse me, it is wrong. It is omega, not x. Okay? It is wrong. Let A is a subset of B, the collection of A. A and B are collections. The collection of A is a subset of B. B is a subset of P of omega. It is wrong. Okay, you must prove that sigma of A, sigma algebra generated by A, sigma of A is a subset of sigma of B, and the lambda of A, the lambda system generated by A is a subset of lambda of B. You don't need to send me the answers. Just ask if you have any question in WhatsApp group. Okay. This theorem is called uniqueness of measures. Let mu1 and mu2 be two finite measures on measurable space omega and f. Finite measure. What is finite measure on omega? It means that mu1 omega is less than infinity, and also mu2 omega is less than infinity. Yes, I told you the definition of finite measure in previous session. Let C is a collection, is a subset of F. F is a sigma algebra, okay? C is a subset of it. F be a P system. What is P system? P system is closed under pairwise intersection, such that F is equal to sigma of C, sigma generated by C. If mu1C equal to mu2C for all C belonging C, mu1C equal to mu2C for all members of C, and mu1 omega equal to mu2 omega, then mu1A equal to mu2A for all members of F. It is clear that C is a subset of F. Mu1 and mu2 are equal together on C and on omega. We must prove that mu1 and mu2 are equal together on whole of member of F. Okay? Its proof is interesting. Please see this section. Let L be this set containing such element of F, A belonging F, such that mu1A is equal to mu2A. Such element of F with this property. It is clear that L is a subset of F. Okay? L, by this definition, it is clear that is a subset of F. We want to show that this L is a lambda system. You must know the definition of lambda system. For the first condition, we have to show omega is a member of F. By this condition, mu1 omega equal to mu2 omega, we see that omega is a member of F, because by definition of L, every A with this property is a member of L. So omega is a member of F. So L has the first condition of lambda system. Second condition, let A and B be the members of L with this condition. A and B are the member of L. So A has this condition, B has this condition. Okay? And it is clear that A is a subset of B. We can write B is equal to A union B minus A. Okay? B is equal to, with this property, we can write B is equal to A union B minus A, and you can check that A and B minus A are disjoint. Okay? Which A and B minus A are disjoint. So we use from this property finite additivity, and we can write mu1B, that is equal to B is equal to this. We can write it's equal to mu1A plus mu1 B minus A, because A and B minus A are disjoint and mu1 is a measure. And we can write this relation for mu2. Okay? We had this relation and this relation. By these two relation and these two relation, we obtain that mu1 B minus A equal to mu2 B minus A. And so, by definition of L, B minus A is a member of L. Okay, here, until here, we see that this L has the second condition of lambda system. Okay, for the third condition, we choose A1, A2, and so on, countable members of L with this property. We have to show the union of AN is a member of L for third condition of lambda system. By the monotone continuity from below. Why we use this property? Because AN an increasing chain. Okay, we have mu1 of union of AN is equal to limit of mu1 of AN, because mu1 is a measure and has this property. Okay, and we know that mu1 AN, every AN, is equal to mu2 of every AN. Why? Because AN, every AN, is a member of L. And by this definition, every member of L has this property. Okay? So, AN that is a member of L has this property, mu1 of AN is equal to mu2 of AN. Again, we use from this property, and we write the limit of mu2 of AN equal to mu2 of this union. Okay, so we obtain that mu1 of this set equal to mu2 of this set. Again, we see that this set is a member of L because of definition of L. Okay. Then we obtain that L with this definition is a lambda system, and we know that L is a subset of F. Okay. Let A is a member of C. By assumption, we know that mu1 of A equal to mu2 of A for every member of C. Okay. We know that every A has this property is a member of L. So A is a member of A. Every A belonging C belonging to L. So we obtain that C is a subset of L. By the previous exercise that I told you is very important. We know that the lambda of C is a subset of lambda of L. The lambda of C by the previous exercise, lambda of C is a subset of lambda of L. Lambda of L is equal to L. Lambda of L is equal to L. By P lambda theorem, we know that the lambda of C is equal to sigma of C. Why? Because C is a P system. P lambda theorem say as lambda of C is equal to sigma of C when C is a P system. Okay, so I write here instead of lambda of C, I write sigma of C. So we obtain sigma of C is a subset of L. We know that L is a subset of F. By assumption, sigma of C is equal to F. By assumption of theorem of this theorem. Okay. F is a subset of L is a subset of F. This implies that L equal to F, and this completes the proof. Why completes the proof? Please see the previous slide. If L is equal to F, then please notice me. If L is equal to F, then for every A belonging to F, we have this property, and this is our assertion, the assertion of this theorem. If L is equal to F, then the proof is completed. Let omega be a non-empty set, F be a sigma algebra on omega. We know that the pair omega and F is called a measurable space. Notice measurable space, this pair. And if mu is a measure on omega, then this triple omega, F, and mu F here, F is a domain of mu. Okay, mu is a set function, is a measure with domain F. Okay, it's called a measure space. This pair is called measurable space. This triple is called measure space. Okay, if in addition, mu is a probability measure. What is a probability measure? You must say me. Then omega f and mu is called probability space instead of measure space. Okay? If mu is probability measure, then this triple is called probability space. You can say me about probability measure. Don't type. Lebesgue measure on R. What is the definition of Lebesgue measure? Here I want you shortly about Lebesgue measure. Shortly, R here in this discussion, R is our main set instead of omega. Main set is R here. In the definition of Lebesgue measure, R is main set instead of omega. This triple R, L, M bar is called Lebesgue measure. This is a sigma algebra, this is measure, this is sigma algebra, this is our main set. Okay, the domain of M bar here is L, is called Lebesgue measure. L, this L that is a sigma algebra is called a Lebesgue sigma algebra, and M bar here is called a Lebesgue measure with this property B of R. What is B of R? B of R is the sigma algebra, Borel sigma algebra. B of R is the Borel sigma algebra. Must be a proper subset of L. Proper subset. It means that it is not equal to L. Okay, it is just a proper subset of L, and L is a proper subset of P of R. Okay, L, what is the name of L? L is Lebesgue sigma algebra. This sigma algebra is called Borel. This sigma algebra is called Lebesgue. This sigma algebra is called power set. Okay, power sigma algebra. For simplicity, we show this Lebesgue measure by M, not M bar. For simplicity, okay. In text, we show the Lebesgue measure M bar with M. Every member of sigma algebra L is called Lebesgue set. Every element of L is called Lebesgue set. Every element of this sigma algebra is called Borel set. Here, we see that every Borel set is a Lebesgue set. Okay, and every Lebesgue set is a subset of R. And then for every interval with this form, closed A to open B, M or M bar is defined as this form. M of this interval is equal to B minus A. B minus A is the length of this interval, or the distance of A to B. Okay, B minus A is the distance of A and B. Okay, M here is defined as this form for this interval, and M of empty set is equal to 0. Okay, this triple with these properties is called a Lebesgue measure. Okay, this called Lebesgue measure. This is Lebesgue sigma algebra, and the element of L is called Lebesgue set, and another properties that I say. Let E be a countable set, then E is a Lebesgue set. Lebesgue set is a member of F, okay, with this property. The mu of E is equal to 0. E is countable set in R. Here our main set is R, okay? E is a subset of R and countable. Then we want to prove that E is a Lebesgue set with this property. Let E has this form with this set be a countable set. We have this equality. The set containing I is equal to this intersection. You must prove this equality. It is easy, okay? See the next slide. Every this interval is a Borel set. Why this interval is a Borel set? You must say me. This interval is a Borel set. The Borel sigma algebra closed under intersection, countable intersection. The countable intersection of such a interval is equal to this set by the previous slide. So this set is a Borel set, and E is equal to this union, okay? And we know that the Borel sigma algebra is closed under countable union. So E is a Borel set. On the other hand, setting an equal to this interval, it is clear that A1 that is equal to Ri, close Ri to Ri plus 1, containing A2. Here you see that the first point is the same, and by the endpoint we see that A2 is a subset of A1 and it is equal to A2 containing A3 and so on. We have a decreasing chain, and also M of this set A and Z by this M of this set equal to, by the previous slide, please see here, M of this interval is equal to B minus A, okay? So the M of this interval equal to I plus 1 n0 on n0 minus I is equal to 1 on n0 is less than infinity, okay? So we can use this property, monotone continuity from above. We can use from this property, okay? Because this condition holds, and then we have the M of intersection of AN equal to the limit of M of AN. What is this intersection? AN is this set. This intersection is, by previous slide, is equal to this set, and I write instead of AN this interval, okay? And M of this interval is equal to AN, this endpoint minus first point equal to this 1 on N, and it is equal, the limit of this sequence is equal to 0. So we obtain that M of every such set that have just one member, the Lebesgue measure of this set is equal to 0. Now by countable subadditivity property, we have M of E is equal to this union. By countable subadditivity, we know that it is less than or equal to this summation, it is wrong. It is not n, it is infinity. I from 1 to infinity, summation I equal to 1 to infinity. Okay, because this union is from 1 to infinity. Okay, you correct it. Is less than this summation. Every term of this summation is 0, so this summation is 0, and we obtain that m of e is equal to 0. And this complete the proof.